thank you everybody for your patience in getting us to this point. We're 10-12 minutes behind a little bit of a schedule, but it's my great pleasure to introduce Eric Peterson, Dr. Eric Peterson, to everybody. So thank you for tuning in. I presume that everybody read Dr. Peterson's bio brief that was in the announcement. So I'm going to let you know a few things that was not in the announcement. His research focused upon separation science has varied from the most fundamental understanding of molecular interactions to construction and proving of pilot facilities using the materials that he has been active developing. He enjoys numerous collaborative research arrangements with scientists from all parts of the US, as well as Europe and Asia. Eric has co-authored 99 peer-reviewed archival articles, 26 peer-reviewed DOE reports, 2 books, chapters, 4 classified reports, and has authored 25 issued US patents, which is dang impressive, with 2 patents pending. Eric's professional affiliations include being a member of 3 professional societies, the American Chemical Society, American Institute of Chemical Engineers, and North American Membrane Society. He's particularly active with the American Chemical Society in 2 divisions and 2 service committees. During fiscal year 2006, Eric served as the National Science Foundation in the Directorate of Engineering Chemical Transport Systems Division, running the nationally visible separation processes and purification program as a visiting scientist, engineer, and educator. His responsibilities included management of $26 million budget, awarding $6.4 million in new project awards, and seeking peer review advice of more than 600 proposals. And I'm going to skip to the most impressive thing at the very bottom of my little thing that I put together. Eric has won more than $1 billion in competitively awarded R&D funding. Eric, the floor is yours.
Thanks, Courtney. Appreciate that. I just caught a typo in my cover slide, which is my last name in my email should be, there should be an N instead of an M. Things get slipped as we go. Anyway, so today we talked about having me talk a little bit about some of the activities I've been involved in the area of rare earth elements, and talk about supply chains, some of the separation science involved, and some of the ongoing opportunities that are coming down the pipe. So with that, let's move on. Just a quick outline of what some of the topics I want to talk about. Introduction to the rare earths, talk a little bit about how they're used, the overall what the supply chain is, how they fit into the markets and their values. And then we'll talk about things from mining and processing and separations and products, focusing primarily on separations. Have a little talk about the future, and then have a summary and an opportunity for you guys to grill me. And if someone has a question, please feel free to somehow bug me. Just bump in if you can. If you can't, we'll do it at the end. So in this, just to talk briefly about what the rare earth elements are. They're the 17 elements at the bottom end of the periodic table, also known as the lanthanides. We also include, for this purpose, scandium and yttrium, because they tend to be considered to be critical. I kind of pulled this picture up of the metals, of pure metals, because I'm always impressed to see them as looking like a metal. I think we all know that they're pretty much have similar properties because of the 4f electron shielding effect, and which causes the lanthanide contraction. Therefore, it's very difficult to get them to do much other. They don't vary in their chemistry a lot. That's the way to say it, because of the contraction. The minerals you find them in include bastnasite, monazite, xenotime, and as I'll elaborate a little later on, there's a few other formats they show up in. And we actually are excited by that because that gives us a whole set of new resources that we haven't had in the past. Next, please. they are abundant relatively in the world. Cesium is like, or not cesium, but cerium is like the 25th most abundant in the crust of the world. They are very scattered all over the place. They're rare because they seldom occur in pure form. And then the alchemists have still part of our world. They call them an earth because you could not really dissolve them in an acid, so they couldn't get them apart to characterize them. So some of the name goes all the way back to the world of alchemy. Next. They're all over the place. And in this map, which is the 2021 USGS map, showing all critical materials as they define them, you'll have to look for those kind of maroon colored squares, but you'll look at them, you'll see some here in Alaska. You'll also see some running down the West Coast. You'll see some scattered around the middle part of the North America, and then you'll see them all over the rest of the world, and especially heavily distributed in both Russia and China and in Australia. Next, please. In the US, we can be a little more specific. You see them dispersed pretty near to you guys, over on the Lemhi Pass area, Diamond Creek, just north of Salmon, Idaho, down in southeastern Idaho, there's a patch of them. And then you look over in Wyoming, the Bear Lodge deposit near Devil's Tower. The biggest one and most active and only mine in the world for quite a while that was active is Mountain Pass. It's now reactivated and they're producing oxides at a pretty high level. They've set records for production this past year. They create a concentrate, which we'll talk about a little later on, that goes on to China where it's processed into metals. But you look at it, they're scattered all over the country. Pea Ridge is an iron mine out in the middle of Missouri, and that's a place where they're trying to get going. They've got some permits issues, but they're coming online. And then even in on the East Coast, there's a few deposits that look likely. They tend to be things primarily in the carbonatite and the phosphate type of materials, but we'll also see examples of other types. Here in Alaska, we have a number of them. There's one called Bokon Mountain, which is getting close to coming online, and as we'll see shortly, they have a relatively high concentration of material there. Next, please. So looking at different resources, let's look at some examples. Bayan Obo is in Inner Mongolia and China, one of the primary deposits that China extracts from. It's an iron mine, and it's carbonatite type of material. You'll see this heavy in what we call the lights. The left-hand half of the lanthanides are called lights. On the right are the heavies. And you'll see that deposit is pretty heavy in the light materials and less heavy in the heavies. However, what's interesting about that is basically you have a cerium mine in almost all these cases. Then you extract all the minor components out of that after you get the cerium out. In Mountain Pass, California, very similar to what you see at Bayan Obo. The Bear Lodge, now we see a drop in the amount of lanthanum and an increase in the amount of neodymium. While we also go on to Bokon Mountain here in Alaska, you'll see a significant drop in the numbers of the light rare earths and a significant increase in the amount of heavies. So that makes it a lot more valuable. We want the heavies because they are used in things like magnets where high temperature stability is required. And then we look at the southern China clay deposits, which are just simply ions absorbed onto a clay material that they desorb very easily. You'll see a large amount of heavies and a sudden decrease in the amount of the lights. So your processing has to be considered very carefully in terms of what you're going to do in order to isolate and purify these things once you get to the separations phase. Next, please. Why are we so interested in these things? I mean, we look at the 2010 markets of metals, and this is a very broad metal marking. We have a $618 billion market in metals that include things like iron, copper, gold, nickel, zinc, the platinum groups, manganese, and lead, and even bauxite. And you get a feel, okay, those are huge markets. And all of a sudden we look at how much the rare earths take up in the metals market. It's less than 1%. It's 0.15% of the total market. but they're valuable to us because they give us stability in our magnets, they give us stability in metals, they are useful in a lot of other applications we'll talk about. What happened that really stimulated all of this interest is in 2009-10, the Chinese and the Japanese had a little problem around some islands are virtually just rocks out in the middle of nowhere that each are claiming. And a couple of fishermen were out there fishing, and the Chinese didn't like that, and they kind of took the fishermen captive for a few days and cut off the supplies of these materials to the Japanese. And of course, that affected their electronics market very heavily. And so they were had a little spat there, and we got a result of a price hike that was tremendous for all of us. And so therefore, the interest in these things and trying to stabilize our resources throughout our country has been a big deal here, and that's why we're so focused on them. Next, please. Let me just take a little sidestep here and just say in 2021, the USGS report identified 36 critical elements with supply risk. And so what they've done is they've taken a look at what's the potential for disruption on the x-axis, and on the y-axis, they've taken a look at the economic vulnerability of these materials. So the further right and further up you are, the greater risk you are. So cobalt, for example, is controlled primarily by Congo. And so they're not a real stable country, and therefore the risk of losing them both economically and in terms of disruption is very high. If you look at something like gallium, it's dependent upon bauxite or aluminum production primarily, and therefore it's really, really hard to get more of it if we're reducing aluminum production, which we did the last couple of years due to the pandemic. There's other examples of these. You can see a dysprosium sitting there on the line. You can also see a couple of the others very close there. Ruthenium, for example, are all pretty exposed. And that's because of their both economic and disruption potential. It's an interesting set of studies they've done here that give us a feel for where we're at with these materials. And if you're further up and left even, it's important to think about that because you start to be feeling very exposed. For example, molybdenum is fairly exposed, and that's primarily because it's vulnerable due to economic issues as opposed to disruption potential. Go ahead with the next slide, please. We also need to look at these markets in terms of their use in production. Let's look at production first. I think we summarized that a little bit, but China produces the vast majority of this material, and they use it primarily. Now, when they say they use it, that's meaning that they're producing higher valued products, value-added product, i.e. metals, that are then used by other producers around the world. So, for example, they'll produce a bunch of metal, which will then go to somewhere else in the world to be turned into magnets. Although at this point in time, that example doesn't hold because they produce most of the magnets too. So they've gotten themselves controlling the value chain all the way up and down. We'll talk more about that in a few minutes. Next, please. So in terms of the supply chain, the Chinese, as I've indicated, control the vast majority of it. Up to 2010, they were controlling almost all of it, everywhere from the basic manufacturing all through, all the way through mining and concentration, controlling all of it because of the way they'd strategically placed themselves in the country or in the world. And so if you look at this carefully, though, in those 5 years, from 2010 to 2015, we began to take back some of our control of the market by getting Mountain Pass running and getting a couple of other mines that got closer to application. And we began to drop some of that dominance off. And in the bottom one, in the bottom chart here, you see some of the ideas. You can see how between 2010 and 2015, some of the markets changed. The catalyst market has dropped a little bit, but not much. The glass market, glass colorant market, I should say, has dropped a chunk. The polishing market has not dropped because we still polish glass, we still polish metals. The metal alloy market has gone up because of all our demand on new metals. The magnet market has done nothing but increase, while the phosphor market is interesting in that it has dropped dramatically, in fact, almost half. And that's because of the sudden and rapid, very, very sudden emergence of LED lighting, which dropped the phosphors in tubes out and caused this dramatic shift in the market unexpectedly. And finally, there's other applications, and we'll talk about some of those in a while. But you'll see the total market of these materials is not very large. And so the total tonnages, I'd say, are very modest. And the problem there that you then run into is you have the opportunity to manipulate the markets very, very easily. So the story of rare earths in this country is controlled by market trends, and you can, well, the costs have been undercut by other countries. And therefore, it's been very hard for us to really get the system going again, though it seems like it's happening right now. Next, please. Some of the applications of these materials, they include things like magnetics, which I've talked about a little bit, things like disk drive motors, anti-lock brakes, frictionless bearings, microwave power tubes, microphones and speakers. Every speaker and microphone we have now has rare earths in it. Communication systems are heavily used all through those, and your magnetic resonance imaging devices, for example. Defense, we certainly use them in everything that has magnetics in it, including things like our guidance systems, our aircraft structures, the metal alloys used in those systems, and some of the smart missiles. For ceramics, they're used in capacitors very heavily, and we can certainly recover them from those ceramics. There's sensors, colorants, scintillators, and refractories. They're heavily used. And examples of those elements that are used there are shown right below each of those topical areas. For catalysts, well, petroleum liquid crackers are primarily the main source where these things go, and they are very heavily used there. That's primarily tend to be cerium based systems. The phosphor area I talked a little bit about. Just about everything we have in lighting now has some chunk of rare earth in there. Every smartphone that we have, every screen we look at, like we're looking at today, that red color is europium. Yttrium gives you some yellows, and the rest are all different colors. Glass polishing, we polish a lot of glass still, and do a lot of pigments and coating with them. My daughter's a pigment chemist at BASF, and she uses them constantly. We have photo-optical glasses that we certainly are using in modern buildings, and then X-ray imaging stuff that they provide the base set for a lot of the X-ray imaging and contrast agents. In terms of metal alloys, things like nickel metal hydride batteries, the M for metal is generally a rare earth. Photocells, steel, we can control the properties of steel that way using them. Super alloys, they provide a lot of strength there. And finally, aluminum and magnesium alloys require a little bit of a flux that contains some of these rare earth elements, primarily yttrium. Next, please. So let's talk about the value chain. The value chain here starts with understanding what you have, what you got out there. So you go looking, exploring. Then you mine it, and then you process, and you get some byproducts out of that. You have to do the separations to get things beyond that. And then from there, you might have some oxide sales. You have metal making. We call it metal making. It's reduction to metal properly, but it's just casually called metal making. And then you get nice metals that you can sell. Or then you go ahead and alloy and produce the alloys that are needed for other applications, and you sell those off. And they go into things, as I've already indicated, magnets, steel, lasers, coatings, electronics, all kinds of stuff. One note though, you can have a rare earth deposit, but that is not a mine. And you can have a rare earth mine that is up and running, but if you don't have a manufacturer to buy it from you, there's no point in having it. So you need to have the whole enterprise from the mine all the way out through making metals to have something that you can actually work with. So those are things we really, really have to consider as you build this value chain up. Next, please. I want to talk a little bit first about the mill and mining aspect of it. So we acquire these things in three methods. We mine them, we co-produce them, or we recycle them. Go ahead, we'll talk about mining first. In terms of mining, there's some exploration you have to do. And once you have done the exploration, you have to evaluate the characteristics of a deposit. You have to then transition that into understanding the geology, and going from the geology, you have to then go into engineering of those systems to make them run and make them work. You are, of course, doing economic evaluations to determine if it is mineable and if it's valuable to you at that point. And once you've gotten that part of it and it looks like it's reasonable, you might go ahead and mine it. You have to develop that mine. And that process, in a very broad brushstroke sense, requires things like understanding what the investment is going to be for milling, what you're going to do to build other infrastructure up, how you're going to dig the hole, and finally, what are the facilities and other activities that have to take place there, and if you can get enough investment to do all of that. Next, please. So in terms of mining and milling operations, well, at the mine level, you have to figure out whether it's going to be surface or underground operations. And of course, these things have all sorts of activities associated with them in terms of what do you do with your tailings? What do you do with impounding? How do you process them? And what are you going to process? What are you going to do at the mine site versus the mill site? Typically, mines will have a mill affiliated with them, and then the separation work often is done elsewhere. So you create a concentrate. In the mining world, you have to get the overburden and waste rock away from the place, and then you have ore that can be fairly rich, anywhere from 13% by weight or more of rare earths. And then the tailings, in some cases, are 0.5% and maybe up to 3%. What's interesting at Mountain Pass is that their old tailings are 8 to 10% in rare earths. That's what they threw away. And the balance of the rare earths they pulled out, they tend to be around 18 to 20% in their concentrations. At the mill level, that's where the process of beneficiation takes place. We tend to do things like grinding and floating and thickening, and then doing some preliminary separations from the gangue material, and then we dry it. And you end up with a concentrate that's anywhere from 60 to 90% in rare earth oxide concentration. And then we go into the extraction process, which will come later in the separations area. And we'll talk about that a little later. Go ahead, next. Co-production is another way we acquire these things. So when we mine aluminum, we get gallium. And that's what this little chart shows, in this sense of what are the co-products when you mine. In copper mining, we get a lot of PGMs and other metals that come out of that. In fact, there was a joke at least a number of years ago when I talked to some friends at the Berkeley pit that they mined copper. Copper paid for the mining, and then the platinum groups, gold, and other elements that came out of it were the profits. So we tie these things together, and we begin to understand that there's a real intricate tie between metal making of various sorts. And also in terms of, as I've indicated, if one decreases, the primary, such as aluminum, decreases, the secondaries decrease. And so you might end up with a shortage of gallium just by accident, because that's where our primary source is today. Next, please. In the world of recycling, that's another way to get them. We can bring them back in out of our current devices where we've invested them already. Let's bring them back and reuse them again. The trick, though, and that's the biggest problem we have here, is how do you collect them? And having worked a fair amount in the area of recycling over the last couple of decades, it's really intriguing how hard it is to pull these materials back. People don't want to have to take the effort to take their cell phone and drop it off somewhere. They just throw it in the drawer of their desk and kind of forget about them. However, today we're starting to see a little bit better opportunity for collection, and people are starting to come around that we can unload these things and reuse them. The trick, once you've got it collected, you've got to dismantle, pre-process, which generally is physical separation of these materials. And today we do things like manual disassembly. We reuse what we can. We remanufacture them if we can, if they can be. And then the balance of the material is shredded and ground up. And you need to worry about, in doing that, we have concerns about things like hazardous substances like lead, mercury, and other flammable materials, plus the flame retardant materials. There are some ozone depleting substances that come out of this. You need to consider how to capture them. And then one of the really big items in the recycling world is the fact that almost everything has a lithium-ion battery buried in it somewhere. And when you're shredding, you create a lot of dust, and these batteries tend to get shredded and then explode or burn. And you get fires pretty regularly in these plants. And they're a real challenge for the managers to run. And then the magnet materials, the Actually, the recyclers hate magnets, and they hate them because they get shredded, they break up, they're brittle, and they form kind of a dusty material, which then, of course, remains magnetic, and it accumulates in the bottom of the shredders and forms these big balls of material that eventually plug the bottom of the shredder, and they have to send a person into the shredder to pull them out. They then pull them out, put them in a bucket, and about once a month, a gentleman from a Chinese company comes by and buys that from them. Therefore, it's not a closed market. The Chinese take them back and reprocess them and send them back to us. Anyway, so then we get into, once you've done that dismantling process, then you process them in fairly standard metallurgical approaches. And we'll talk a little bit about that as we go further out. There are examples of commercial rare earth recycling going on today. They're tied up with companies like Erecover out of Belgium. They recycle just about anything they can get that has electronics in it. They pull out the platinum group metals and gold and silver, and then they take the rest of the slag off of that, those valuable metals, and sell that off to a secondary company also in Belgium that then recycles the rare earths, or purifies and separates the rare earths for reapplication. So there is recycling going on, but it's very, very limited, and it's pretty hard to get done because of the cost. Next, please. One example, of course, is the cell phone, since we all hold one of them pretty much every day. And the components in them are things like motors and the LCD screen, the integrated circuits, all containing things like gold and platinum and palladium and silver, nickel, rare earth elements. And the average cell phone today, in today's market, is worth about $5. Just about $5 is what it's worth in terms of the metals in it. The challenge remains, how do we get that collection system to come together? And how do we get our social network to come together well enough that we can pull this off? How do we get enough collected so it's economic? And then how do we get the extraction technologies to keep up with what's coming? These things are ever changing. And so it's really difficult to set up a process that will do just recycling of cell phones, because even they change, or electronics for that matter. So there's a big movement right now out there in both the academic and some industrial circles to look at how to design these systems for recycling. And stay tuned for that. I think it's a really exciting topical area that's coming forward. Next, please. So let's talk a little bit about the processing side of this thing. We've gotten through the exploration, the mining, and the pre-processing. Let's talk more about the details in the processing, the separations, and even a touch on metal making for a few minutes. Next. And this slide really kind of feels out of place. I think we've addressed most of what's in it, but I'll repeat a couple of things. One, the ore grades come in from less than 1% to about 15% by weight at the time of mining. And you can either have open pit or underground mining. We concentrate through magnetic, gravimetric, and flotation approaches to get 50 to 90% rare earth content by weight for bastnasite, which is a fluorocarbonate. And monazite is a phosphate mineral, which we tend not to process much lately these days, or haven't traditionally done, because monazite tends to contain more of the radioactive materials. And then I indicate the 90% you find when you process the ion absorption clays in China. These concentrates are mixed in that they contain mixtures of all of the rare earth elements in the ore at that time. So there's no real separations going on, but once you have the concentrate, you're then ready to move on to separations. And here's the real, I kind of think with the next slide, please. Here's the real key to where we're going in this talk. In the area separations, these are the major methods used. There are some others on the periphery, but these are the major methods used to do separations on these systems. There is the solvent extraction, which we'll talk about. There's membrane solvent extraction, which is called MSX. There's a typo there. There's crystallization processes. I'm not going to discuss those because they're there and used by some people. Supercritical fluid extraction, which is primarily an R&D activity. Membrane filtration, we'll talk a little bit about that. There's biological processes, there's ion exchanging processes, there's solid phase extraction. A few of you probably know as much as I do about that, since that's a Montana technology. And there's also Erecover Process, which is a new one that's just coming to bear today. So let's go ahead and next slide. And as I talk about a couple of these things, several of these things are related because they're tied to solvent extraction in some way, shape, or form. In the sense that we are chelating these elements, or we're binding them ionically. We're finding some way to grab them with some specificity. And there are things like cation exchangers, which are primarily focused on carboxylic acids and or phosphorus acids. They're functionalized in different ways in order to make them soluble in different solvents. There are diethyl phosphorus acids as well that take part in that. There are chelating exchangers such as the beta diketenates that are pretty effective in it for actually doing the chelation. And then there's solvating extractants such as the phosphorus ester materials that solvate, basically grab them and solvate them based on their polarities. And then there's anion exchangers based on primary amines. And so as we go through this, we'll be able to talk a little bit about which species we're trying to get and what of these specific items we'll use to do that. Next, please. In terms of separations, let's talk about the solvent extraction first, or SX. It's been around for decades. We take these acidic solutions where we dissolve the material out of the ore or out of the concentrate, and then we use the multiple mixer settlers to get these things to happen. Now, and I'd say the extreme for this is probably at the California site, where they have taken these materials, they dissolve them up, and then they run these 500 to 700 gallon tanks where they add the solvent, which is kerosene, the extractant, which is dissolved in the kerosene, and then you take the metals dissolved in the aqueous acidic solutions and you mix them together. And the metals are pulled from the aqueous solution into the organics phase. And there are probably 2 buildings the size of football fields on that plant site with at least 50 to 100 of these massive tanks in each of the buildings. So it gives you a feeling for the scale of the place. It's huge, it's immense, and it smells like kerosene a lot. So you have to have, in order to do these fine splittings of these elements, you have to have dozens of these stages, and you have to have just hundreds of square feet of this material to get it to happen. What has come about are some things that are pretty intriguing. In time, we've developed a variety of different mixer settler configurations, one of which is shown in the lower right side there. It's an all glass example where one uses smaller mixer settlers in tandem and or a series to achieve the same effect as the very, very large tanks and tank farms. Therefore, splitting this or decreasing the size of your footprint to a point where it's, you take it from being multiple square, football-sized buildings to being the size of a common everyday house by doing this. Shown on the left side is the new upcoming UCOR facility located, I believe, in Ketchikan, Alaska, that is coming online to do these separations, and they're using like 40 or 50 gallon tanks rather than 500 and 600 gallon tanks. And in the center of the diagram, of course, is what I've explained as being the mixer settler concept, where you strip the metals out, and you get fairly high efficiency by doing that. So you extract the metal from the organic phase into the aqueous phase, you scrub it to be sure you've got it all as much as you can out, then you strip it out of the organic phase back into the aqueous phase using pH shifts and things like that to make it happen, generate a pH shift. Go ahead, next please. And this gives you a feeling for what the solvent extraction looks like. We take it through in multiple stages. You do an initial split of the metals in the first stage, and this shows the way that the folks at Mountain Pass, California do it. where you go from the mixture to lanthanum, cerium, and praseodymium, and lights and heavies, basically, praseodymium, neodymium, and samarium. And then they do a second split using a slightly different chelating complex to drop it out into lanthanum, cerium, and cerium praseodymium. And then finally, we take and split out lanthanum, cerium, and praseodymium, and then neodymium and samarium, if you really want to go that far. It's commonly done where you sell a couple of these as basically as mixtures because that's acceptable in the markets today and written into the specs of what magnet makers require. So you don't have to go to elements in all cases. Next, please. Another way to approach this is a kind of not a herring, but a different way of approaching membrane solvent extraction is by adding a membrane in, or a porous membrane that contains the solvent extractant, and you then run your material over that, your feed solution across that solvent extractant that's contained in the membrane, and you run your stripper on the other side. And basically the solvent extractant becomes your transport medium for these, for the elements. And so you take a unit operation from a two-step unit operation into a single-step unit operation. And you're then able to recover the rare earths in much less time, much smaller spaces, and it's proven to be exceptionally efficient. That process has been developed and commercialized over the last 4 or 5 years by a company in collaboration with Oak Ridge in Idaho. Next, please. You can then also hook these units up both in parallel and or in series to give you very efficient collection of material. Shown in the left side, the current neodymium recovery, for example, is over 80%, and the kinetics are incredibly fast. So we've achieved that in less than an hour, coming to equilibrium and pushed it up to 80–85% recovery. The kinetics of the capture are very, very fast, shown in the left side of the 4 diagrams on the right. And then on the far right side, you can see the release kinetics are pretty reasonable. So we get the materials in, we get them across the membrane, we get them out pretty quickly. These do require clean streams. You have to have a fairly well filtered stream before it goes in, so there's not a lot of particulates hitting the membrane. 2 reasons. 1, the particulates will get stuck on the membrane and foul it. And 2, they'll, if you're using high face velocities, which this requires, they'll tend to erode the surface of the membrane and destroy its selectivity and release the organic. So there's some tricks to how you run these, but you can run these and they do work very efficiently. And this process is being licensed by a couple of different mining companies right now. Next, please. Supercritical fluids have also been used, at least thought to be used for these systems, and they've been tested at the bench level in several cases. For example, in batteries, some of the nickel metal hydride batteries, they've been able to generate, you dissolve those up after they've been expired, and you supercritical fluid extract them with extractants that we normally use in chemical extractions for solvent extraction, and you're able to perform the same, get a very similar result without the organic phase. You substitute the organic kerosene phase with supercritical fluid carbon dioxide. And then a couple of folks have taken some concepts here. This is a conceptual drawing I show in the lower right, and taken that and turned that into a concept where we include a very porous membrane as a separator and do countercurrent flow extraction using supercritical fluid carbon dioxide. And we've seen some real good success there in terms of getting it to a pilot phase. I haven't seen it go and commercialize it yet. Partly that's due to the cost of the supporting hardware to maintain supercritical fluids. So we'll consider how that goes in the future. Next, please. Other standard membrane systems have been proposed and actively pursued over the last 50 years, roughly. I've been active in that area for at least 25 of them. And so membrane processes, of course, are pressure difference, electropotential, chemical potential, and temperature difference approaches. And they've been proposed for doing everything from water purification for flotation, pregnant liquors, concentration, lithium ion, pulling lithium from brines, other metals, pulling metals from waste, recovery of reagents, and I don't remember what AMD stands for, I'm sorry. But all of these things are potential uses of membranes. Polymeric membranes tend to suffer with things like durability and selectivity maintenance and fouling issues, as I've indicated previously. So you need to think about it. The stainless steel, porous stainless steel / ceramic composites tend to be very effective in this field and have been used extensively. And I'll be talking about them briefly here in a while. Go ahead, let's see what the next slide says on it. Yeah, and then let's talk about biological processes. There's a lot of activity in this area for bioleaching, and we've been very successful in using biological processes to pull gold out of systems. They're doing it down in Nevada all the time today, as well as pulling other metals out of their bedrock process systems, where the microbes generate acids right at the surface. The metal ions are mobilized, and then once you have the metal ions mobilized, you can capture them by other means. And then there's also been some effort to separate them using biological processes as well, by selective precipitation and or separation of individual rare earths. And it's interesting to see what we can do. I'd say this is an up and coming technology, although it is implemented in some places. So it's something to keep watching. For the rare earths, it's still growing. Next. Ion exchangers are of course an area we work in a lot, and some examples here. I won't. The slide here is pretty detailed. I'll go touch on a few things. Most of the big ion exchangers are based on divinyl benzene, and the skeleton I show is the skeleton of the polymer is shown in the next little step there for the skeletal framework, and then we functionalize the system in those areas. One of the big achievements in the last decade has been the use of engineered fractal distributors to make the large-scale use of ion exchange effective. The trick is that these swollen polymers are very sensitive to both thermal and pressure gradients, and they tend to compress with any major offsets. Using fractal distributors, you're able to get even pressures going in, even pressure coming out, and you can run huge amounts of fluids through them at very high flow rates and still get good capture of metal ions. And this example of an ion exchange column on the right is used in the sugar beet industry, and they have fractals on the top and bottom, and they have the ion exchanger for softening the beet juice in the tank. And they're able to run 700-800 gallons a minute through these things. So it's a huge amount of material running through these things. The trick, though, is you have to maintain temperature at a very modest amount, and of course, not have offsets of pressure. So next, please. So an alternative to that has been developed in a couple of different places, one of which is Rich Hammond with US Metals in Missoula has been very successful in developing the solid phase extractors, where we stick take the liquid extraction systems and stick them on to polymers, tie them down, tie them onto surfaces, and start to work with capturing materials in chromatographic-like settings. This is a system that has worked well for him. He's demonstrated it, and I believe that has had a fair amount of success at selling it in terms of an alternative to standard ion exchange. A couple of folks have developed some other ways of doing this by sticking different ion exchanger-like systems directly onto the silica surface. And if you stick it on a silicate surface directly and covalently bond it there, you are then able to have much higher temperature stability in those systems and pressure stability. Shown here is an example of a beet juice softener, which took a tank. Well, I'll show you in a moment. We took the tank from 8x10 down to 3x3. So it's pretty exciting. Next, please. We engineered a fractal column where we took the column and turned it into that box, which is 3 feet by 3 feet by 2 feet, running 700 gallons per minute through it, using engineered fractals. And in that upper photograph on the right, you see the clear rinse juice, rinse water over the juice, which is pretty dense, which is kind of brown, over the top of the solid phase exchanger. And that's running at 700 gallons per minute, constantly pushing it through. It ran for at least a decade, well, I won't say a decade, at least 4 years that I know of. And last I knew it was still running with water at temperature 90 degrees Fahrenheit, or not Fahrenheit, centigrade. So it was accomplished where you could run very hot solutions and not have to cool them before you hit the ion exchangers. Next, please. The Erecover process is a new process that has been developed recently for dissolving metals out of electronics and or ore. Both have been demonstrated and piloted. Things like gold, silver, platinum, palladium, zinc, lead, nickel, and the rare earths. And whereas in the electrode cell or electrochemical cell, one has an oxidizer that they generate. So you're generating in situ your oxidizer. You're circulating that over a column of your rare earth and metal containing systems. You allow that to corrode or dissolve your materials out, and you drop it into a tank where you have your recovery electrowinning process as your other half of your electrochemical cell, basically. And it has been remarkably successful and is currently licensed to industry. We are able to recover approximately 90% of the metal content, and the costs and wastes are reduced because you don't have large chemical material, you don't have large chemical stocks sitting around because you're generating them in situ. And it has been carefully evaluated and is under the license process right now, I believe. So exciting. This is an exciting new step in this separation area. Next, please. So let's talk a little more about the downstream processes, and there's not much here. I'm going to keep it brief and fairly simple. So next, please. In the world of metal making really is the reduction of these of oxides and halides to full metal, just to the metals. And there's of course smelting, which you all well know in Butte, in terms of metallothermic reduction, using either a furnace or various molten salt processes. You can use oxygen, sulfide, and carbonates as your reductants. And then what we tend to reduce is what we pull out of the separations process. They're either chlorides or fluorides. We can reduce oxides, but that's a little more expensive and preferred to do with other things. There's fused salt electrolysis of rare earth chlorides or oxide fluoride mixtures, which is commonly used in China. It's dirty, but it works. And then there's Erecover, which is an R&D 100 winner, as I've talked about earlier, and it has been demonstrated for this purpose as well. One of the newest areas in research that is being worked on today is doing electroreduction in ionic liquids. And it's really interesting as long as you keep your ionic liquid scrupulously dry, you can actually do the electrowinning of the metals directly out of the solutions. So it's a big step if we can make it happen. And it's a pretty exciting research effort that's ongoing today. Next, please. In terms of alloy production, alloys are interesting things to produce. And I didn't put much there because I think you all know how to make alloys. What I did say is, how do we fabricate these things? Well, we can forge them, we can roll them, we can extrude them, we can put them into sand casting, die casting, all sorts of different ways of casting them. And then there's also a lot of powder metallurgy in these systems. And in fact, when you get down to magnet making, a lot of magnet making is powder metallurgy today. So I just wanted to add that as something we do. It's not really within the scope of this conversation, but it's something that we do, and it's interesting. Next, please. So when you get done, what do you get for products? Well, you get things like the catalyst. The upper left photograph is an example of a fluid cracking catalyst that are just going into production. When they come out, they're coked, and they're black. and they're ugly, and they're considered a hazardous waste, and they're buried. So we don't have a lot of those around anymore. You can do glass additives, so you get these beautiful colors of glass. There's also polishing compounds, such as the multicolored group in the middle of the group of photos on the right. There's metal alloys, where I show a metal alloy being poured in the middle on the left. And then, of course, there's phosphors that give us lots of colors in our CRT screens, our current flat panel screens, and in our most commonly thing in our cell phones. And finally, there's magnets that we are very interested in, are a very large market share of rare earth elements today. And so I throw a magnet in there. Next, please. What are the potential environmental impacts of these systems? Well, in the world of mining, there's things like overburden and waste rock and sub-ore stockpiles and ore stockpiles that we have to worry about. What do they offer you? Well, they have a lot of radiologic materials in these you have to worry about, things like thorium and uranium. You have metals of different sorts, other metals that we don't necessarily want to have around or in circulating. You can have acid mine drainage. You can have dust and all sorts of associated pollutants that affiliate just with the mine. In the world of processing, you have grinding and crushing and dust of all sorts. And then, of course, radiological materials there too. You tend to get stuff in water. You need to worry about that. So you get turbidity of your water. You have organics that you have to deal with that come out of these mines. And you also have dust and associated pollutants that we really, really need to be watching carefully. And finally, in the world of recycling, well, there's all kinds of stuff. I think I talked about a lot of it. It's things like dust and organic vapors and metals and organics we have to keep track of. And then during the processing, you have to, again, track down things like volatile organic chemicals, dioxins, other metals you may liberate but don't want to. You have to catch them and get rid of them, but you have to catch them. And then some trace organics I indicated earlier. Those are some things that we think about for environmental impacts we have to really guard as we do these processes. Next, please. In terms of looking at the future of these systems, I show here a diagram that was put together in 2011. And ironically, I just saw another one that came out from another source that looked just identical to it. So I stayed with the older one because I have it, and I would have to redraw the new one. And what's interesting here is that you see that the Chinese exports have dropped off dramatically. The rest of the world demand is going up. China's own demand is increasing dramatically. And so in those gaps, that's where the real opportunities are. And there's opportunities to make our separations more efficient, to obviously make our mining and processing more efficient, and then to finally figure out how to make our metals more efficiently. So there's lots of space here to do research and to really grow our markets in these materials. Next, please. Let's talk briefly about what resources are coming online, and that'll help to explain what we see coming. Mount Weld in Australia is just come online about a year ago and is running at full power. Mountain Pass, California is back up and running. So there are two big resources for the world that are coming. Ucore is getting ready to build, is getting ready to build its processing facility in Ketchikan, Alaska. And they're getting ready to open up Bokan Mountain. That's misspelled, B-O-K-A-N. And then the U.S. Rare Earth in Arizona is in process of developing their mine. Rare earth resources in the Bear Lodge of Wyoming are in the process of looking at mine development. The U.S. Rare Earth is also in Wyoming. They're doing some mine development. Research, the Western Rare Earths guys in Arizona have a mine in process of being developed and a new process for processing the systems. Again, it has solvent extraction in it, so it's a derivative thereof. There's a group outside of Montreal that have got a project under development, and it's basically an old iron mine. There's a group named Wilbur Land and Cattle Company in Oregon that are working in volcanic tuffs right by I-5. It's about like a mile off of I-5, and they're up and running. They're processing material. They're they're basically a gravel pit, but they've got relatively high content of rare earths and some other elements in their system that they're trying to develop, but they're processing materials and already selling concentrates. So there's some exciting stuff going on out there. Lots of people doing interesting science, interesting engineering, and interesting mining. And there's others that I didn't even talk about in this process. Next, please. So where are the opportunities today? And I've listed just a half a dozen that have come to mind recently. The Department of Energy, fossil energy, has a pilot plant processing RFI on the street. I think it's either just closed or going to close shortly. And it's for about $140 million of contract R&D to build a pilot plant for processing rare earth elements. The Advanced Manufacturing Office, AMO, of DOE has ownership of the Critical Materials Institute, which is a 10-year-old, $250 million currently spent effort in rare earth elements. They're going to rebid that in 2023, and it's looking to be about $100 to $150 million effort over 5 years, and then maybe more in the future. The DOE Fossil Energy Core Critical Materials, or Core CM program, that stands for Carbon Ore Critical Materials, is got $120 million out there awarded and split up into 13 centers. They call them Technology Innovation Centers. Montana is a part of those. I'll show you in just a minute the list, but that's out and awarded. Department of Energy Office of Science has project-based basic science work going on in rare earth purification, separations, applications work, not so much applications, but understanding the basic science. The National Science Foundation, CBET, where both Angela and myself served, has some project-based stuff going on, and I think there's a few things going on in chemistry as well, but I'm not sure how much. I didn't look that up today. The DOE, another part of DOE called ARPA-E, has some project-based efforts going on. And then, of course, Department of Defense has some novel approaches to sourcing questions coming up. And they've got a couple of RFIs and RFPs out there. So those are some examples of some things that we're going to be watching and thinking about. Next, please. I wanted to briefly tell you about the Carbon Ore Critical Materials Program, just to let you know that have an idea what this is about. The core CM program, as it's known, focuses on trying to help different regions build their ability to take carbon ore, which is better known as coal, and pull the other values out of it. Since coal is kind of dropping in value in terms of our energy generation, how can we use carbon ore or coal and pull the valuable resources out of it? And when there have been a number of basins identified, proposals written and awarded on the topic of how to pull rare earths out of coal. Next, please. And this is the list of the core CM centers. You'll note that I've highlighted that Montana, and I do not know which school in Montana or schools are involved with the University of North Dakota and University of Wyoming to generate this, to work in this area. The University of Alaska has the Alaska Basin, and that's a combination of University of Alaska Fairbanks and Anchorage working together with a bunch of industrial partners to generate a technical innovation center for working on Alaska-based coal. Next, please. This is your turn to ask me and grill me all you want. Thanks a lot for your time.
Thank you, Eric. I'll open it up to questions, and please unmute and ask away. Ooh.
Lots of questions, huh?
Rick, go for it.
Hello, Eric. Thanks for the talk. I just had a question. I don't know if you're, I guess I'm more pulling your thoughts on it more than anything. So MP Mountain Pass, they just signed an agreement to produce magnets for General Electric or General Motors.
GM, yeah.
Do you have any thoughts on that? Talking about bringing the supply chain back to the US and thoughts on success of that or anything?
Well, Mountain Pass is Mountain Pass is a unique place. They at one point were the supply chain, right? They were the supply chain for the world pretty much. They have all the capabilities to do anything they want to do. Some of their facilities are old, they're outdated, but they've been aggressively rebuilding that plant from the ground zero. And I think their chances of success are quite reasonable as long as they are able to compete at some level against the rest of the international markets, and or we're willing to pay the higher price for those products.
Thanks, Eric.
Yep.
I'll ask one and hopefully start enticing others, Eric.
Sure.
Speaking of environmental issues, any thoughts on thorium and perhaps getting involved in thorium nuclear reactors?
Oh boy. That becomes a political question. That's what that is. And I think we all know that. Let me suggest, I think we need to do it. I think the reactors are fascinating to look at. I think they would be valuable and useful to us. India is pursuing them, I believe. And I think that we owe it to ourselves to at least look at it. Now, we're bound by treaty, as I understand it, that we will not concentrate or purify thorium. So we have to we would have to understand and figure out how to work with our treaty partners to allow us to continue to work with that material. But yes, I think it's an exciting area. I think we should work with it. Today, it's handled by backblending. At least the strategy at Mountain Pass, I'll say, is to backblend those materials into their waste pit. So we're not allowed, by treaty, we're not allowed to go over, I think, 8% or 9% of concentration of those materials. And so they backblend it as it goes out the back door into the pit. And so they always keep it below 9%, I think.
So they just put the thorium tailings back into the pit and just bury them.
Yep.
Okay.
So, if you wanted to really get enticed by something, you could look at the waste pit, just the waste piles, I'll say, at Mountain Pass. And they're probably a world-class rare earth and thorium mine today. That's how much they threw away there. And there's other places. I mean, there are places where there've been a lot of placer mining done, where you can, and in Idaho, there's several places where there's big brown piles of stuff left over from the placer mining guys. And that's almost all monazite. Think about that. Monazite contains a lot of rare earths. Now it's radioactive, but yeah, you can handle it. And you can actually, once you crack the monazite material, you can probably get some pretty valuable stuff out of there. There's some world-class piles of material sitting around that are waste products that we could actually go back and remine. The phosphate plant. All the phosphate plants have a tremendous amount of material in them that can be accessed and used as well, if we can get through the EPA process to open those piles back up.
That was actually my next question, Eric. Was about the phosphate sources of rare earths and sort of what you thought about that.
Okay, try the question again. I don't know what you're asking me.
So I was going to ask about I saw there was a recent article on mining.com about rare earth mining out of phosphate tailings, and I was just curious what your thoughts are on the possibilities of that.
They're really good. There's a lot of material in there. If I recall the amount of rare earth in phosphate waste piles in Florida, Pocatello, Idaho, and one other plant, I've lost track of where that was, combined is enough to supply the world for like a decade or 2 decades. Okay, that's how much rare earth materials in those waste piles. The problem, the challenge is not the technology to get them out. We've demonstrated that. Critical Materials Institute group, the group at Oak Ridge, demonstrated that you can pull the rare earths out and do it pretty efficiently. The challenge remains, how do you open up those piles? Now, they also have looked at integrating processes along in the production process for phosphate and pulling them out before they go into the pile, and you can do that. So you can think about it any way you want. You can get there. If you can get there from here right now, if you want to. It's just a matter of who applies the technology and how much cost you're willing to incur to get there.
So
Thanks, Eric.
US rare earths used to be looking at Limhi Pass. Is anybody looking at that anymore?
Yeah, they are.
Okay.
They continue down that path, as I understand it. They were a year ago. In fact, now let me see. I just read something recently about them. They were looking for permits on both the Idaho and the Montana side. I mean, as you well know, it sits right there. The border is there, and there's all these piles of gray and black and brown rocks there. They got a permit from Montana to do preliminary, not drilling, they've already drilled, do preliminary, what do you call it, prospecting, I'll call it, on the Montana side. And that, I believe, is what they're doing right now.
Yeah, I've been encouraging our legislature as best as possible to at least get them to build the plant on the Montana side. They can mine in Idaho, but we want the plant.
Yeah. You want the plant. You want the plant in your state, and I think there's more water on your side if you go down off the divide on your side than there is on the Idaho side, honestly. And you'll have better access. I think you have better access getting to it because of the Salmon River being such a fishery. They're not going to let you in there. But yeah, they also have, I believe they also have Diamond Creek, which is the deposit just to the north and west of Salmon. That's old growth forest, so it's going to be tough to get in there. But you can walk up in there and you can see, again, the stripes in the ground of the brown dikes in the granite. So pretty amazing. The concentrations are not high. They're a marginal resource, but they're still pursuing it and should be.
Good. A political question for you. Do you think the private sector is going to come through, or should the federal government get involved in subsidization, or a combination of the two?
I feel that we have to subsidize in order to make this happen. We cannot compete against some of these other countries in terms of wages that we pay versus what they pay. But I also feel at the same time that we have to find a way to do it in an environmentally normal and environmentally sane way, whereas most of these other countries are not following environmental practices that preserve the nature of the environment, i.e. the rivers and the streams. You've seen what China's done to their rivers. You can only imagine what Vietnam is doing to their rivers. So I think that we need to be very cautious in that, but yes, I think there should be a combined effort, both private and government sectors, to make it happen. And we're seeing that come along slowly but surely. The amount of money that's going to be pumped into it by DoD, I think, is amazing. And I think it's going to be a wall of money hitting to get some of these supply lines focused here in the U.S. and made domestic.
Are there any more questions?
I mean, I can keep asking questions all day, Courtney.
Courtney, this is Jim Kevich. Is there a chance we can get a copy of this?
I believe, Jim, that it'll be archived and you can access it through a Montana Tech website.
Okay.
Susie Anderson, she can kick in a better answer than mine.
Yes, so it will be available online through Digital Commons, and I believe also you'll be able to access it through YouTube as well. It just is a matter of getting the recording and Eric's signed permission to post. So it'll probably be a week or two maybe before it's accessible.
Okay, thank you very much.
You bet.
I'll update a couple things and resend it to you guys.
All right. Rick, go for it.
I had to add one more question. I know on the Critical Materials website, maybe about a year ago, they were talking about some lock cycle flotation testing that was done that showed 70% recovery or so. And I'm just curious about your feelings on the validity of flotation as a way to concentrate rare earths. Because we did a bunch of flotation testing here at Montana Tech, and it was not supremely effective.
Was that Critical Materials Institute, or who was that?
Yeah, it was the Critical Materials Institute. There was, along with the Core CM, there was another call that CMI put out.
Yeah.
Around that time. So it was around the same time that the Core CM call went out.
I'm not aware of the work, so I really can't comment too broadly. I don't know what was done or what was claimed. So that's a new one to me.
Okay, thank you.
Yeah, I can't comment on roles unless I have the data, and I haven't seen it.
It's just more on, I guess my question is more on, is even the flotation is the most common concentration step, but there is difficulty given rare earths, diffusion in the ores and the particle sizes needed to obtain liberation.
Yes.
Is flotation the correct concentration step?
That I can comment on that. That is, and I think you already answered the question. That is ore dependent. I've been seeing a lot of very highly positive results with in the area of coal, material coming out of coal, which is heavily iron. It's got a lot of iron around it, and the materials coming out of some volcanic deposits. I see a lot of magnetic pre-concentration being done. That's very, very successful, much more so than flotation. So again, I think it's ore dependent, and I think it's also process dependent. What are you feeding? Where are you feeding it next? But the result we see with some of these others, yeah, we're seeing magnetic seems to win in multiple cases.
Yeah, I know RER is abandoning flotation, and they'll do a magnetic step and go into oxalic leaching.
Yes. Yeah, they're looking at revising their flow sheets tremendously. I think they got dragged down a couple of different paths that weren't quite weren't quite normal. And I think they're having to reevaluate a lot of their processes. I hope they're looking at you guys for help.
Jay Picard's there is a Montana Tech grad, so he reaches out to us.
Good. Yeah, they got, as I say, they got dragged down a couple of paths that were kind of funny. So I hope he can help them.
Thanks, Eric.
Yeah.
And I'll stop asking questions now.
You don't have to stop, Rick, but Eric, to comment, you showed that slide with Montana in red. And yes, that is Montana Tech, and I think MSU as
Okay,
well.
Good. Well, maybe we'll try and, we already have connections with Nevada, or no, North Dakota rather, and Utah through the Alaska system. So maybe I'll try and extend up to